Hello and welcome back to Physics by the River. I'm Junaid, a maths and physics student, and I'm joined today by Ben.
Hi Junaid, it's great to be back. Really excited to be here, and it's going to be hopefully a really interesting episode today with a really interesting guest.
Yeah, we're joined today by the one and only Professor Jens Funke. How are you doing today, Jens?
Well, I'm doing great. Thank you for having me, Junaid and Ben. And I'm really looking forward to talking to you about math, physics, research, and maybe even life.
Oh, that's great.
Okay, well, I think to kick off, could you tell us about your research in automorphic forms and number theory?
Yes, I guess I could. But first, I would like to advertise that there was something completely different, and that is, what did you do this morning at 9 o'clock? You weren't at the park run, I suppose, which of course starts right here at Maiden Castle and is great fun, and it's good for you instead of, lying in bed in whatever state you are this Saturday morning at 9 o'clock. Right, so after we got this out of the way, yes, indeed, I'm a number theorist, and there are various branches of number theory. There is algebraic number theory, which attacks number theory questions via algebra, and variations there of arithmetic geometry or algebraic geometry, then really via geometric means. There is very much analytic number theory, where you throw, in the broadest sense, complex analysis at your problems. And then there is a third area, which is somewhere in between and everywhere and nowhere, and that's the theory of automorphic forms and modular forms, which tries to some extent combine this. I would argue it's one of the increasingly central topics and themes and methods in number theory. And so in its most basic incarnations, so-called modular forms, at that stage I currently teach this for the 4th year, so everyone who wonders what they should do next year or in 2 years' time, do take the modular forms course in the math department. It's generating series, it's Q series, which some of you might have encountered in combinatorics or otherwise, where the coefficients of your generating series have number theoretic meaning, but on the other hand, the function itself displays a remarkable symmetry as a function of a complex variable, and you study the functions which have these kind of transformation properties, the symmetry properties, and with this knowledge about these functions, you can then say something about the coefficients of your generating series, the combinatorial number theoretic object.
Oh, that sounds really interesting. So what kind of implications does this have for things beyond theory? Are there kind of applications and things that this research is helping to
so develop? Applications, if you want to, within the theory was, of course, in the early to mid-90s, Andrew Wiles's proof of Fermat's last theorem, which is, of course, some of you will know the equation, the generalized Pythagoras equation, a to the n plus b to the n is equal to c to the n. A, b, c are integers, and n some power, and of course for n equals to 2 we have many solutions, infinitely many. Can you do this for higher n? And of course Fermat asserted you cannot. And he was a lawyer, so meaning he didn't give us really good argument, but so that took us then 350 years roughly to solve this problem. And what is remarkable is the entire power of 20th century's mathematics had to be thrown at this problem. And at the very end of it, in the 80s, people realized that this had something to do with modular forms, automorphic forms, and would be a consequence of a conjecture which was made some decades ago, which is very, very important to us. and relating so-called elliptic curves to modular forms. And and at the very end, the argument went down, well, if there was a solution, then some kind of modular forms would need to exist, but it doesn't. And I mentioned now elliptic curves in this. So modular forms, or in the elliptic curves, are crucial for internet cryptography, or particular mobile file cryptography.
Oh, that's really interesting.
So there is a very close relation to this. There are actually some connections to graph theory, and very, very deep connections to theoretical physics, which some of them are older, but in particular in the last 10 to 20 years became very, very evident.
Oh, that's really interesting, because I think we've mentioned before a bit how research can often be quite abstract, and something like this, that kind of you're researching and it doesn't necessarily have a particular meaning in terms of like tangibly with kind of technology and things. But then as we move forward with things like internet cryptography, as you mentioned, that suddenly is something that's moving quite fast at the moment, and we then look at all this research that's been done previously, and suddenly there's things that jump out and are helpful that we could never have been dreaming of using in this way, which is really interesting.
Well, indeed. This is of course, I'm a mathematician, hence I'm biased. This is, of course, the unreasonable effectiveness of mathematics that, curiosity-driven research just follow our imagination, and sooner or later this will be good for something, will be applied, except one cannot quite predict where it will be, what will it be good for. But I basically do this because I enjoy it.
Oh, that's the most important thing.
Yeah, for sure. I think it's quite interesting also how with things like Fermat's last theorem, with the a to a n plus b to n equals c to n, like even if you have quite the intuitive understanding that maybe there won't be any solutions, like it seems quite apparent, like even in like with our elementary understanding of number theory in second year, like we look at proving it for n equals 3, like there's no solutions or stuff, we did something like that. But then showing, like sort of generalizing it can actually be much more difficult.
Yes, that's right. It's moreover the Fermat equation, which you could argue, well, who cares? Except, of course, it's there, and you want to climb that intellectual mountain, is that it has served, the Fermat equation has served as a motivation for quite deep developments in mathematics. Sophie Germain in the early 19th century did some remarkable work on this. And then Kummer in the 1840s, he made a bit of a breakthrough, and the math historians are not quite, or at least I'm not quite aware what the latest research on this is, whether Kummer thought he had actually had a complete proof. But very quickly it became apparent that his approach would not be able to give the Fermat's last theorem, at least not that easily. But in that course of trying to fix his idea, which was a great idea, he invented ideal numbers, which then turned into ideals. The notion of an ideal, which all second-year students in algebra know, is the ideal of a ring, in a ring. So, and that was a truly great development, and that continued to be the Fermat equation inspired people to produce great mathematics.
Yeah, it's really powerful how one piece of research or one big question that so many people are curious about and trying to answer can lead to so many other branches of mathematics and so many new ideas being generated. And I think there's something really powerful about that. It's like one question as simple as, can we generalize the Pythagorean equation, it can lead to so much, is something quite astounding.
Yeah.
Yes, it is. Maybe having done this now for so many years or even decades, I might take it now for granted, and you just pointing this out makes me aware that I maybe shouldn't take it for granted, and should be as excited about this as I was at your age as a student about these questions.
Yeah, that's really interesting. Another thing I wanted to ask was because mathematics is quite a different discipline to other scientific disciplines, because rather than being evidence-based, it's all proof-based, and it's possible in a way that it isn't with physics or chemistry to be able to prove something conclusively for all of eternity, and that proof will never go away. And I just wanted to ask you about kind of your thoughts on mathematical proof and kind of how that's different to other disciplines.
I mean, you're of course right. Mathematics as a deductive discipline is very much based on the notion of a proof, and of course striving to derive the results by logical arguments going back to the axioms. That all said, still mathematics is carried out by humans. So and hence a proof is always also a social construct, as in a theorem is proven if you have been able to convince other people that your argument is watertight and works. And as such, this notion actually of a proof, what constitutes a proof, actually has changed over the, if you want to, since Euclid, when people realized, well, say, looking at this 50 years or sometimes 500 years later and saying, well, that's a bit of a gap here, isn't it? But then we go back to this and keep working on it. So it's for the moment it's fairly stable, what we consider proof, except for that developments in the last 20, 30 years is where we increasingly rely on computer proofs. Mm-hmm. At some point, if you want to slugging out the remaining 2,300 cases, say for the proof of the four-color theorem, for the listeners, so the four-color theorem is the theorem you have a map with your countries and so on, and of course you want to color your map. Each country should get a different color. Well, no two adjacent countries should get the same color. And how many colors do you need at least? And it's fairly simple to see that 5 would do, but then at the end there was the four-color theorem proven that 4 would always be enough, and the original proof was reducing it to several cases which were then checked by computer. Now, this was, if you want to, the early uses of computer-based proofs. Now the development goes further and basically actually have machines and algorithms proving theorems by themselves, or even in some cases even finding them. It's a bit of a frightening prospect, but probably you will see the day when machines will be better in finding and proving things than human beings.
That's something really quite scary, almost. That computers could kind of reach the point of being able to do that. Yeah, that's really exciting to think about how that could change over the next few decades and centuries.
I don't know, I find it kind of reassuring, like, I'm sure the computers will make a lot less sign errors than we do.
Yeah, the computers have a bit more accuracy than a human. Yeah, because with proofs, I guess there's a big question of someone presents you a proof, is it correct? And how do you go about kind of verifying someone else's argument or kind of something that they're trying to assert? What's the process with trying to verify whether someone else's proof maybe misses an edge case, or if there's a slight problem with it that's difficult to spot potentially?
Well, I guess my first instance, I just try to read it, which sometimes can take a long, long time. And of course, this is not safe. I referee a paper for a scientific journal, so that's peer review. Colleagues of mine would submit a journal to submit an article to a journal, and then the editors of the journal ask other colleagues, peers, to review this. And at some point, an article might end up on my desk to be reviewed and to be checked. And this sometimes can be very time consuming because, as you point out, you want to make sure that the paper is correct. How do I do this? If it's a long paper, you cannot read every single line. You need to apply your expertise and to identify some arguments or also some results where you say, well, I'm not quite sure about this one. And then you would dive in. Of course, there are several reviewers often for a paper, and this is not foolproof. And occasionally, something isn't quite right. Usually it's rather the result is probably still right or sufficiently right, and there's just a gap. And if it's bad luck, the result is actually wrong.
Does that actually happen often, where someone publishes a proof, but then it turns out that what they thought they ended up proving isn't correct?
Well, it happens once in a while. I'm not sure how often it actually happens. When it actually happens it is as embarrassing as it is exciting, because there's something new to be understood. I remember some 25 years ago in differential geometry, there was some classification result which stood for, I think, even decades. And then one grad student, actually one PhD student, actually read through this and didn't understand an argument, kept digging, kept asking, and then it turned out to be, no, there was a big fat gap, and there was one class of objects existed which people didn't think they were existing. Oh, and that turned into a very nice PhD thesis. So, but that an entire theory collapses because something down there is completely off, that I'm now not quite aware of.
Yeah, that's really fascinating to think about how the implications of that can lead to lots of new research and other branches of research, which is quite exciting in a way.
I also, however, need to say is that there's also, at least to some extent, in a development in the different direction. If you want to moving away from proofs, say that in areas of mathematical sciences, which I may say closer to applications, say for example statistics or machine learning and so on, where they're relying less on proofs and more focus on the applications of this, if you want to more of a physics approach to things. And this is equally valid. I mean, the mathematical sciences is much larger than just pure mathematics, even though I'm representing pure mathematics and keeper of the faith of the proof. One needs to acknowledge that there are other approaches to mathematical sciences.
Oh, absolutely. I think maths isn't obviously just about proofs. It's kind of almost, it's a language to facilitate a lot of other branches of science, is how I sometimes think of it. And it's quite a useful tool to be able to think about everything else. I'm not trying to say that it's the God subject, but it's quite helpful. It can do a lot.
Well, I need to be careful what I'm saying here. Yeah, of course you're right. And to also then say it, I think it was Gauss, the one and only Gauss, who said is that mathematics is the queen of the sciences, and number theory is the queen of mathematics. Thank God I'm a number theorist. No, seriously, going back to the number theory, is one of the appeals of number theory is that we use every tool available.
Mm-hmm.
So we use algebraic methods, we use analytic methods, we use geometric methods, topological. We use every tool which is in the arsenal of the mathematical sciences to prove our results. So from that perspective, I like to think that number theory is one of the really truly central topics in at least pure mathematics.
Mm-hmm.
That's quite interesting to hear, because from my very entry level sort of opinions on number theory, I would have thought it's just a very sort of niche branch of mathematics. I wouldn't have considered it the queen of mathematics or whatever at all. Really, I thought it was quite tucked away, just using simple algebra. I feel like this has been a controversial statement.
That's a very controversial. I fear that there may be altercations from this. Oh, yeah. I think it's one of the things about maths is that every branch and every kind of field of research within maths gets used by every other part of maths at some point, and they all end up being linked together and in a really interesting way.
First of all, Jeanette, you need to be careful what you're saying. You don't want your guest to walk out midway through the program.
No offense.
No, of course not. So, but Ben, you're right. This is one of the features, and for me, this is actually a characterization of interesting, good mathematics when it's no longer pure in the methods, as saying as well, oh, this proof isn't great because it uses some tools from some other area, but it's rather characterization of the strength or the general interest of it.
Mm-hmm.
Because then it has connections to other areas, implications, and then usually the exchange goes both ways.
Yeah, absolutely.
Which is, by the way, also one of the remarkable features of mathematics in its relationships to physics.
Mm-hmm.
I know this is a physics program, so I also need to be careful that what I'm saying is that I won't get thrown out for you.
We would never.
Well, you don't quite know what I want to say. No, it is rather remarkable how physics and mathematics interact and enrich each other. Is in the last 10-15 years, my research, which I was absolutely sure had no connections to physics whatsoever, is in the last 10 years I start to hang out with a theoretical mathematical physicist, research-wise. Just last summer I participated at a 2-month research program in Cambridge at the Newton Institute, and the title was Physics and Number Theory, Building and Crossing the Bridge.
Mm-hmm.
And this quite stunned me in various ways, even though I was in abstract aware of this, that modular forms, automorphic forms have close connections to physics. Very roughly, if you have some physical state and you can form some partition functions thereof, where you count some states parameterized by positive integers, you write down the generating series, and then you hope it's a modular form.
Mm-hmm.
And remarkably often it actually is, but if it isn't, then you want to measure how far it is away from it. And this actually happened you all, well, most, or certainly the second year students will know Professor Anne Termina next term in AMV. So in 2010 or 11, Anne showed up in my office. I had no idea why she would, and so on. And she said as well, Jens, let me explain you something. Yeah, and she explained then that 3 mathematical physicists from Japan had written down the so-called elliptic genus for K3 surfaces, and wrote down this whatever that is, and realized that this had something to do with the representation theory of the so-called Mathieu group. Right. I kept looking at her. Said, well, and then she said as well, Jens, you remember monstrous moonshine? And I said, of course I do. And they says, well, it appears to be that this is a new case of so-called moonshine. I will say a few words about this in a second. But this time, the object is not the modular function, but rather a harmonic weak mass form, which were objects which I co-invented 10 years before that meeting. So I was rather stunned, and this still hasn't been properly understood. So what is moonshine? So in the 60s and 70s, people embarked on the classification of all finite simple groups. It's something which, if you want to think about groups or simple groups as the atoms of algebra, and trying to classify them all. And they knew, or at that point they suspected, quite didn't know, but suspected that there was a monstrous object out there, which they hadn't found or constructed yet, but they already gave it a name, the monster group. There was also a smaller one, which is known as the baby monster. And they didn't know whether it existed, but they knew their properties. And one of the invariants of that object involved the number 196,883. Fine. Except that there's an object in modular forms, the so-called Klein's J invariant, which also comes with certain numbers, and one number there is 196,884. And when this was explained to John Conway, the superstar at Princeton, and one himself, he looked at this and said, "This is crazy. This is moonshine. What have you been drinking?" So since then we call this kind of phenomena moonshine, and this was then proven by Borchertz, for which he received the Fields Medal in the 90s, and in particular it uses methods or inspiration from mathematical physics. So out of nowhere. So now we have Mathieu moonshine, we have umbral moonshine. There are other forms of moonshine now, which I have now forgotten, and we continue to be amazed.
Oh, that's great. You always hear about like maths being used to propel physics forward, but I haven't really heard before about physics sort of pushing maths forward before.
Well, there's all sorts of things in the natural world, particularly, that are kind of there's questions about things like geometry that crops up naturally, that evolution has kind of made happen, and trying to explain some of the things that are going on with maths is using it the other way around, and it's interesting how that sort of thing can go both ways, as you say.
Oh yes, no, absolutely. I'm in particular, since this is a physics program here, I happily acknowledge the importance of physics to mathematics, but also to my area of research.
It's on the record now. You can't take it back.
Yeah, well, I've been advised that I should be diplomatic.
Yeah. So I wanted to ask you, Jens, about the history of maths, which we've kind of talked a little bit about. But what would you say is the importance of learning about the history of the development of maths when learning about maths? Is it enough to just learn about the results and kind of all the things that we know, or is it also important to know about how these things have been developed and the kind of the human stories behind them?
I suppose you could just learn mathematics just by, in a certain sense, how we do it. We present you the things how they are now and how we understand them now, and as such, if you want to, this represents the state of the art, and this is what we should do, and we will continue to do so. When I teach you, or in the Analysis 1 course last year, and I had great fun explaining a bit about the historical developments, or even sometimes some of the human stories behind it, then I do this is, first of all, it's fun, but also to give you a bit of a broader understanding that mathematics is not that monolithic block. If you want to, yes, there are the results once they're proven and they stand there for eternity, that there is a development, and there are things which needed to be understood, and people didn't quite understand them. So, whatever that notion is, the notion of uniform convergence, which was then, in particular by Weierstrass, championed in the, I suppose, 1840s, which really was that his predecessors, there were some aspects they haven't quite understood yet. And well, that didn't mean that the work of Newton, Leibniz, Cauchy, Euler, and so on was invalid, but rather is that there was a further development. And because the arguments the predecessors of Weierstrass and so on made, they were still valid, but they had a bit of a gap which needed to be addressed, and things moved forward from there. So I would like to get in this, and also if you want to, the variety where things are coming from. Mathematics it's a very, very global enterprise currently, but of course in the past mathematics wasn't invented by white Europeans. It's much, much older and much more fundamental than that, and trying to get you a bit of a sense of this aspect as well. I mean, the human nature, I suppose I really tell this just for fun.
Yeah, I think it adds a whole new level to mathematics teaching, particularly at university, where it's quite different to high school, and it's not just about here's how to do sums, here's how to get these results. It's learning about about how this has all come about, and kind of some of the stories behind it. And I think that's really interesting to add into a university course.
Yes, I think so, but I have to admit, I really do it for the fun of it. Of course, I care about quite a bit of the history of things, so that's I have to come clean here. That's my real motivation. That said, let me make some other shameless advertisement. So currently, in the Tunstall Gallery in the castle at University College, there's an exhibition on Bishop Tunstall. And why there is one is because in 1522, so exactly 500 years ago, Tunstall published the first printed math book in the first math book printed in England, exactly 500 years ago. And he does elementary mathematics. He does also, if you want to, word problems and all kinds of things. And based on this, colleagues, and I was involved in this as well. So we contacted the castle, the university, exhibition team, but also the society, Society for History and Mathematics here in the UK. So we had a symposium on this in September, where Tunstall and his work was discussed, and there's lots of things there to learn. And also about the person Tunstall, who was not just the bishop and then later the Bishop of Durham, but he was actually a European scholar. He studied in Padua in Italy and then returned, but he was very well connected. He had connections to Erasmus of Rotterdam. He corresponded with Thomas More. So he was exactly part of this gang. And then he wrote a math book. And the first printed one, and this one is so, which everybody, all listeners, please embark on a pilgrimage to the castle, and even if you're not a member of University College, and have a look at Bishop Tunstall, the person, the mathematician, but also the politician. The early half of the 16th century were quite turbulent times under Henry VIII and his successors, and Tunstall managed to survive them all, just about. Though.
Yeah, that's really interesting. I'll have to go and check that out. Thank you.
Okay. Earlier you mentioned that you do mathematics almost purely just because of the love you have for it. So could you maybe mention a bit like why mathematics attracted you as a discipline more than, say, physics or anything else?
Oh, with physics, that's very simple. I never cared about physics.
Wow, I see.
No, I can understand that. I can sympathise with that.
All right, okay. So that said, it's on the way here to the studio. I actually thought about this and get the basic question: why on earth did I study mathematics? And the story I'm telling you now is a bit. It's almost alarming, really, and as it is maybe even moving to some extent. Is basically, I knew that at age 5. All right, this is the story is told by a friend of my parents, and of course you're at some party and they ask you, what do you want to be when you're grown up? And of course you want to be a fireman, a policeman, or a professional footballer, these things. And apparently little Jens said, I want to be a mathematician. Right. Well, and so I am. So I did become a mathematician. However, it's really alarming because at age 5 I could have not possibly grasped what that could have possibly mean. Mm-hmm. So that was a thought which was really put in my brain by the grown-ups. Yes, I was very good with the numbers, could count and this and so on, say a year or two before others. Still, that idea was planted in my head by grown-ups when I was 4 or 5 years old. I did think about whether I should have, back then when I was 18, had to go to uni and so on, whether I should study law instead. And to the great dismay of my father, I was accepted also to study law, and then I ditched this and went on to study math.
And the world was better for it.
I'm not sure whether the world, but I think I did fine.
Durham, if nowhere else.
Oh, Durham, if nowhere else, has become a better place for it. Yeah.
That's quite interesting. Most people don't make their mind up so early. I think I was still considering launching an artistic career at age 5.
I don't know what I thought back then. I don't think a career was really on my mind. I least of all maths. I think it's fascinating that you clearly have such a deep love and passion for maths. That I think that's great.
Yeah, I was more looking towards becoming a Pokemon trainer at that age.
Wow.
Well, this is of course not my age, but I suppose conceivably you could have a career, by now you could have a career in this. As a Pokemon trainer.
I think it'd be quite hard.
You'd have to be inside a video game, Junaid, and I don't know how easy that is at the moment. Give it a few centuries. They might develop the technology. Well, I don't know. I don't follow the technology. I don't follow it.
We'll just wait for the innovations in maths and physics, and then my dream can become a reality.
Well, and maybe even your studies might be helpful for it.
Maybe.
There you go.
That's my motivation from now.
Wow.
Gonna make the Pokemon trainer dream real.
Yeah. So what motivates you to keep researching new things in maths, Jens? Is it just the curiosity of answering questions, or are you motivated by kind of the applications as your work kind of has connections with physics and technology, and that becomes more apparent, or what motivates you the most?
No, I don't know the applications. This doesn't motivate me. I do pure research, curiosity-driven research. I do it first of all. I'm simply curious. I want to know, and it's fun. And in particular, it's fun since I'm not doing this alone. I have a set of collaborators, the interactions with them. This is really, to a good extent, which motivates me. I'm not rarely sitting all alone in my study, in the office, or wherever. Look, I do this with, and if you want to, even sometimes for others. So for me is also mathematics as a social discipline. It's so much more fun if you do mathematics with one or two other people. When you stumble along, you make mistakes, you fix it, and then you see the light. I guess this is why I'm doing this. It's fun, and in particular, it's fun to do it with others.
Yeah, we talked.
And apparently, it's even good for something.
Yeah, I mean, if that happens, if it has a use at the end, then that's a bonus. That's great.
Well, it's I'm of course overdoing this. I'm very much aware that the things I'm doing are relevant, or will become at some point relevant. Hopefully, also by educating others, you or having PhD students. I actually have one former PhD student who now works at a place which shall not be named in Cheltenham. So it's and I have a few mathematical brothers, meaning other students of my PhD advisor who work for the NSA in the US.
Oh wow!
So there's also this aspect of things. And I don't know, and I don't really want to know, whether my actual research is actually considered by them.
Yeah, you don't necessarily need to know. You can do research for the sake of curiosity, and I think it's wonderful to be able to do that, as well as being able to do it motivated by all sorts of applications in various fields. Yeah.
Yeah, we talked about the social aspect with Daniele last week of it, didn't we?
Yeah.
It's nice to hear that it's sort of a common sentiment. It seems that the sort of communal aspect of academia is one of the highlights.
Absolutely. So you had Daniele Torrigoni here last.
Yeah.
Oh, right. Yeah. So first of all, I'm upset that you had him before me. But second of all, of course, Daniele is one of the mathematical physicists who are not often, but on a regular basis discuss this, and he was also in Cambridge over the summer. And more than once Daniele asked me a question about modular forms, or present me some insight, and this is from his angle.
That's great.
Yeah, so so Daniele is exactly one of the people I would talk to on the physics side.
Oh, that's so nice to hear.
Yeah.
So what then at the end, what made you study math? Well, mathematics or physics?
I would say for me, it's that curiosity of being able to answer questions and understand the question by translating it into this this language of mathematics. And there's often so many different approaches you can take to answering that question, by considering it from different angles, and approaching it using all sorts of different tools, and how everything is surprisingly linked, as we've mentioned earlier, about how different branches all contribute to one another, and that to me is something that's fascinating, that all these things that seem like separate ideas are somehow linked, and they're all one and the same, and that's something that's really powerful, and I can't wait to kind of see where my studies can take me with finding out more about that.
Excellent.
For me, I would say, I guess it's the sort of fundamental nature of maths and physics. Like, you can have an intuitive understanding of how the world works. Like, you jump, you come back down, but it's not until you kind of get the mathematical modelling that you get with physics that you can say, okay, well, I can predict exactly how fast I'll be coming down, things like that. And then also, this is more physics and maths, I suppose, but with things like cosmology and astronomy, we really can sort of build understanding of where we fit in the universe. And I think that's just really interesting.
It is, but if I may say so, we have the Hubble and now the James Webb telescope, and they're producing this spectacular photos, but of course much more than that, also spectacular insights. But then sometimes I do wonder, we see photos of a supernova, of a star blown up, I don't know how many million light years ago. And I wonder whether my integers, as monstrous as they might be, when we might ponder the question, how can we factor an integer with 200 digits, or my modular forms, whether that's more real than a supernova from how many million years ago?
That's all very much a matter of philosophy. I think it's really interesting how human nature can be kind of captured by the curiosity of either something in the galaxies that happened so long ago, so far away, or something that is kind of so abstract and arguably doesn't really tangibly exist in the world, and all of these things that kind of make people think, and you get all these kind of stories about the history of research and kind of the direction that all these brilliant minds have been taken. I mean, there's Euler and Gauss, the two obvious examples that spring to mind, who goodness only knows how they were thinking about so many things all at once, and captured by kind of the curiosity of it all. I think that's something really powerful.
Yes, indeed, but no, there's no but. Just saying is, you should also maybe mention Ramanujan in this one. He was the man who knew infinity, and quite a bit of the number theory and modular forms research was driven by insights, or if you want to, assertions Ramanujan made in his notebooks, or even in his letter to Hardy and his work together with Hardy. You might have seen the movie, The Man Who Knew Infinity, and the question on the partition numbers. So a partition of 5 are all the ways how you can divide 5 into a sum of smaller pieces. So 5 plus nothing, 4 plus 1, 3 plus 1 plus 1, 3 plus 2, and so on. And it's clear that they're finding many possibilities. So you have the partition number of 5, 10, of any other number, of any number. And you like to have explicit formulas for this. And there's a nice recurrence relation, which, however, becomes very quickly really intangible to handle. It simply doesn't work. partition number of 200 is already monstrous. These numbers go very, very quickly in the movie, and that's actually all what happened. And there's Major Maroon, I believe, computed this, but Ramanujan said there is a better way of doing this. Writing down an infinite series, which, however, the first few terms are so close already to the answer that they give you a better way of expressing this. And there are congruences which Ramanujan found and actually proved. In August, when I was in Cambridge, we made a pilgrimage to the Wren Library at Trinity College. Mm-hmm. Yeah, we were supposed to see some stuff in Newton. Yeah, Newton, fine. But then there were also the original manuscripts, also the so-called lost notebook by Ramanujan, and the librarian got it out. We were allowed to touch it. We couldn't believe it. And reading it, it's immaculate handwriting. He was actually there in the mode of actually deriving things. Also, Ramanujan's last letter to Hardy, the so-called Mach theta functions, which we now finally also understood, or to a large extent standards by research on automorphic forms, and I'm glad that I was able to contribute to this as well. It's so never forget and underestimate Ramanujan in this.
Yeah, absolutely. It's important to remember all sorts of people like that. Yeah, absolutely.
It must have been very interesting to get that sort of direct insight into how someone like that, who has clearly such a deep understanding of mathematics, sort of thought.
It was to some extent, being at the library, seeing these manuscripts, holding that. It was almost a spiritual experience. And occasionally I do wonder whether I should have studied law or something else. But these are the moments when you realize, no, I didn't study the right thing.
You made the right choice.
Yes, indeed.
Oh, it's great to hear. Yeah, I wonder how they had such a deep understanding. Maybe they got the runner's high from a park run.
I strongly doubt it.
Never know. Okay. Well, it's been great talking to you, Jens, but our time is very sadly nearly up. So I think maybe it's best that we wrap up here.
Okay.
Yeah, that sounds like a perfect note to end on. I think it's great to have moments like that can really inspire you, and that's great to hear about.
Well, I have to thank you for having me. It was great fun indeed.
Yeah, thank you very much.
Yeah, thank you. Do you have any last advertisements that you want to plug before we sign off?
Well, when you're fourth-year math students, do take modular forms.
Yeah.
You heard it here first, folks. Modular forms is the way to go. Thank you all for listening, and we'll be back in 2 weeks for more Physics 5 Over.